So in our previous video, we looked at the rules for significant figures and applied them in this case to 6 example numbers of what digits in a particular number are considered significant or not according to the rules. So what are these rules actually grounded in? Partially they are grounded in the idea of rendering a number into its kind of shorthand known as scientific notation, and that is a base 10 exponential value. So scientific notation is a shorthand way of representing long and unwieldy numbers, and it is a base 10 representation because counting is done on basis of 10. We move placeholders every time we are in a multiple of 10, so that makes complete sense. So scientific notation generally has a coefficient, a base, and an exponent. And of course we can write this in the E notation that a lot of us teachers prefer. This is simple, but this is the same thing as that. And in scientific notation, what do you round the coefficient to? You round it to its number of significant figures. Now we are starting to see why these rules work. So the number 6 million, these trailing zeros are not significant because I can easily replace them in scientific notation. Here is the equivalent value, and I can undo this and turn it back into a normal number. We have no loss of precision, no loss of accuracy, so to speak, here. Similarly, here in B, we know these leading zeros are not significant. Why? Because we can easily replace them with notation. And because this is a fractional value, we are having this 1, 2, 3, 4, we are moving this decimal 4 places and so forth. So we can see how trailing and leading zeros can be replaced in notation. And that is why they are not significant. If I said turn this back in a normal number, we would turn it exactly back into this number. We would have no loss of the accuracy of the number whatsoever. That is why they're not significant. They can be easily replaced in this shorthand, either in the traditional way of doing scientific notation, or if you want to write it in the E notation. It's the same thing, people. So we can do this, but the basic rules of scientific notation are when we turn a number notation, we always put one digit after the leftmost non-zero number, and then we trail it with the remaining significant numbers. And that, if it is a number greater, than 1 or greater than 10 or what have you, then we're going to have a positive exponent. And if our number is less than 1, we're going to have a negative exponent. And we'll have a separate video just on doing notation value, don't worry. But those zeros are easily replaceable. Here, of course, it is impossible to replace this zero. We can't do that and still have the number come out back to itself. We have to basically keep that zero in there, because if we took out that zero, we would not be able to return our notation back into a normal number. Similarly, here on exercise D, we can't get rid of those zeros because we are assuming that these are actual placeholders representing the accuracy of the measurement. Let's say that this was grams. This is like basically saying that I'm able to measure to 1,000th of a gram here. It would not work in this case. That would not work because if we put that back to this, then we've lost those degrees of accuracy that were implied here. This would be basically saying that the measurement was only to 1/10 of a gram, and that's not reflecting what actually happened. So that wouldn't work. We actually need to retain those trailing zeros if we are trying to show truly the level of accuracy of that measured value. So this stuff isn't in a vacuum. It's meant to be representative of real mass or real volume or real time or real length. So you have to remember this makes sense only in the context of real measurement, people. So let's go ahead and wrap this up E and F if we wanted to turn these into notation. Once again, I can't chop these values if these are actual measured values. If they really represent something that was truly measured, then it would make sense that we need to retain those trailing zeros. We can get rid of that leading zero and make this 8.309000 times 10 to the negative second power, because I can turn that back into this easily, and it's still the same number, okay? But the trailing zeros we would have to retain. Whereas over here, on this case, this last number right here, we can drop those trailing zeros because we are not concerning ourselves with, like a precise measurement that's a fractional value, because we can undo this and it will go back to that number. So this takes a little getting used to understanding, like, what's this all about. But once again, it's about trying to represent accurately real measurement in real time and space that really happens in a lab, whether it's on a scale, whether it's in a graduated cylinder, whether it's with a clock or with a ruler or what have you. So it starts making sense once we start putting this stuff to work in a lab and we have to punch something in a calculator, we get some unreasonable number that doesn't really reflect what we were actually doing. At what point do we cut off the number? So that's why we do this. And we'll continue to work with significant figures and scientific notation until it kind of becomes, a basic part of your scientific understanding.